Now, using these properties, you can prove the geometrical formula for the dot product amazingly. Just based on these properties, suppose you didn't know anything about the geometric formula for the dot product, it actually follows from these properties. And this proof is really beautiful. So I don't normally do that many proofs, mathematical proofs in physics 1, but this proof is so beautiful that I can't resist showing it to you. All right, so okay, so let's take this, and it's also a good exercise in everything that we've learned so far. So suppose I have a vector A and I have a vector B, and they make an angle theta, right? And suppose this vector, which goes from the tip of B to the tip of A, is the vector C. Can somebody tell me what is the relationship between the three vectors A, B, and C? I think, yeah, go ahead.
Vector C plus vector B equal vector A.
B plus C gives you A, that's correct. So B plus C gives you A. So A is equal to B plus C by the triangle rule of vector addition. And which means that you can just move you can solve for C and write it as A minus B, right? So you can write C is equal to A minus B. If you that just means moving the B to the left side. Everybody with me? So that is the relationship between these three vectors. Let's take the dot product of this equation with itself. So C dot C must be equal to A minus B dot A minus B. So I'm just taking a dot product of this equation with itself, right? So now what is C dot C? So from the properties that we saw earlier, the dot product of a vector with itself is nothing but just the square of the magnitude of the vector, right? So C dot C I can write as just C square. And notice that I'm using the convention that if you write the symbol without the arrow on top, it just refers to the magnitude of the vector. So C dot C is just C square, right? Okay, let's simplify the left side, and let's just FOIL the left side. So I get A dot A minus A dot B minus B dot A, and then plus B dot B. That's what we get on the right-hand side, just by foiling it. And how do I know that it's okay to foil? That is because we've already proved that the distributive law works. So that's why it's okay to foil, right? We can't assume anything works, anything that we can't assume any of the rules from our ordinary scalar mathematics translates directly. We have to be really careful. But this one will work because we know we've already proved that the distributive law works. So that means it's okay to foil. All right, so let's simplify this a little bit. So C square is equal to A dot A is just A squared. B dot B is B squared. So I can just get that out of the way. And then I have a dot B and a B dot A. Now I know that A dot B is the same thing as B dot A. That's something that we've also proved because we know that the dot product multiplication is commutative. So A dot B is the same thing as B dot A. So I can write this as minus 2 A dot B. That makes sense? Or I could have also written it as B dot A, but I'll just go with A dot B, right? All right, now let's just pause this for a moment. Let's pause this calculation for just one moment. And let's just look at this triangle purely geometrically. So what we have here is a triangle in which one side has a length A, another side has a length B, and the third side has a length C. And the sides A and B make an angle theta. Purely geometric fact. It's just a triangle here. Now, for any triangle, there is something called a cosine rule. Are you guys familiar with the cosine rule? Does that ring a bell at all? The cosine rule gives you a relationship between the sides of any triangle. It's true for any triangle. And the cosine rule goes like this. C square will be equal to A square plus B square minus 2 times A times B cosine theta. So if A and B make an angle theta, then the relationship between the three sides of the triangle will be c square is equal to a square plus b square minus 2ab cosine theta. Have you guys seen this at some point, the cosine rule? All right. One special case of the cosine rule is when theta is 90 degrees and you have a right angle triangle. So what is cosine of 90 degrees?
0.
Yes. And so what will this equation become when theta is 90 degrees? It
Well,
will be, yeah, go ahead.
Pythagorean theorem.
It will just be become the Pythagoras theorem when theta is 90 degrees. That makes sense? So the cosine rule is a more generalized version of the Pythagoras theorem, which applies when the angle is 90 degrees, not 90 degrees. So anyway, so let's apply the cosine rule to our triangle. So according to the cosine rule, we get c square equals a square plus b square minus 2a times b cosine theta, right? That's also true because this is the cosine rule. So we found two different ways of writing c square. So let's set them equal. So if you set these two equal, you get a square plus b square minus 2a dot b, which is what we got from vector analysis. That must be the same thing as a square plus b square minus 2ab cosine theta, which is what we got from the cosine rule. So this came from vector analysis. And this came from the cosine rule. So now you can see that the a square and the b square cancels out. The minus and the 2 also cancel out. And you get, amazingly, a dot b is equal to magnitude of a times magnitude of b times cosine of the angle between them. Isn't this beautiful?